Hey guys, I want to talk to you today about how weight and balance works. And to understand weight and balance, we need to understand that what we're essentially talking about is a torque. Okay, a torque is a twisting force, T-O-R-Q-U-E. It is a twisting force. And to understand our twisting force, we are going to need to know, okay, our force, and in this case it's going to be a weight that is going to be pushing down on something, and then we need to have a distance for that weight to act over. So distance, and we are usually going to use inches and pounds for our distances and our forces. And when we put our inches and our pounds together, what we get is some sort of a force, like if we were to use a torque wrench or something, and maybe I'd have an 8-inch long wrench and I need to put 10 pounds of force on the end of that 8-inch long wrench. Let's draw that. Here's a bolt. All right, here's my wrench. It is 8 inches long, and if I put a 10-pound force on that wrench, I get 8 times 10 equals 80 inch-pounds of twisting force on the nut. And I need to know that because when I start talking about things in weight and balance, I'm going to be talking about twisting forces. But instead of talking about twisting forces that are going to twist a nut, I'm going to talk about twisting forces that are going to twist an airplane. So here I've got an airplane, and this airplane is more or less stable inside the air, and as long as everything is balanced properly, and it can be thought of as balancing on its center of gravity. And if I put something in the front of the airplane, well, let's say maybe I put a bunch of oil into the front of the airplane. As I add oil to the front of the airplane, it's going to try and twist the airplane forwards. Now, there's lots of things trying to twist the airplane forwards. The engine's trying to twist the airplane forward. The propeller's trying to twist the airplane forward. All kinds of things are trying to do that. But the airplane is balanced if all the twisting forces to the nose are also counterbalanced by twisting forces to the tail. And that's where this process gets a little bit confusing. So probably the best way for us to consider this, to start looking at it, is to consider that we have a lever. Let's just draw a simple class 1 lever, or I'm going to call it a teeter-totter instead of a lever. So here we are, and we've got ourselves this teeter-totter. And this is our fulcrum. And on our fulcrum, that's where things are going to begin to pivot. And if I were to put a box on this teeter-totter, and I don't know what we're going to call this, just for the sake of argument, let's call this box B, because I'm going to put a box A on the other side. In that box B, I need to know 2 things in order to find its twisting force. I need to know its distance, which I'm going to call distance B, and I need to know its weight, which is just going to be however many pounds this box is. And I can find out how much twisting force this would put on my lever if I multiplied, okay, we can call this twisting force, in this case it's going to be this way, is going to be equal to weight B times distance B. I'm kind of running out of space, sorry about that. My weight B, I'm going to write that a little differently. I'm just going to write it big B times little b, because that's going to give us a little more space on that. And if I've made my weight in pounds and I've made my distance in inches, that's going to give me a twisting force in inch-pounds. And by the way, that twisting force has a special name. That twisting force is called a moment. All right, and its moment is equal to, in this case, big B times small b, and it's in inch-pounds. And that's what happens from this box right here, box B. Now, if I were to leave this like this, if I were to make this arrangement just like this, the teeter-totter is going to twist over that direction, and it's going to fall on that side. But if we wanted this to balance, we would need to put another box over on the other side, or another weight of some kind. Let's go ahead and put another box on this side. I'm going to make it look a little bit different, but I'm going to call it A, and box A has a weight of A, and it has a distance of little a across here. Now, What do I have to have in order for this box, or this pair of boxes, to balance on my teeter-totter? I don't think it takes a rocket scientist, sorry about the phlegm in there, I don't think it takes a rocket scientist to note that our moment from A, which is going to be trying to twist the board this way, to force everything off that direction, must be then equal to our moment from B, which is trying to twist this way. All right, so we can have our moment A is equal to our moment B, and if that's the case, these are going to balance each other. Now, I happen to know that I can have a big weight and a small distance, or a small weight and a big distance, and it will still be able to balance everything out. And I can actually calculate that out by putting some numbers associated with this. Let's not call that A anymore. Let's call that, oh, how about we say B is 10 pounds, and it is 10 inches from our fulcrum. And we can come over here to A, and we can say A is 5 pounds. There's our 5. And it is X inches. All right, so my twisting force due to B, or we'll call it moment of B, is going to be equal to 100 inch-pounds. And that's why I chose 10, because it's nice and easy to do the math. I've got 100 inch-pounds twisting my way this direction. For this to balance, I know that I have to have 100 inch-pounds going this way. And to get 100 inch-pounds going this way, this was my moment A. My moment A must also be equal to 100 inch-pounds. And everything is going to balance. But how do I get 100 inch-pounds if my weight is 5? Well, in this case, I'm going to move down here so we can see all of this. In this case, I have 5 times my distance X is equal to 100 inch-pounds. And so, if I have 5 times X is 100 inch-pounds, I'm going to divide both sides by 5, and I get X equals 20 inches. All right, because that happens to be 5 pounds, 5 pounds. My pounds cancel, leaving me with 20 inches when I do all of that. And now I know how much it's going to take to balance a 10-inch box, a 10-pound box 10 inches away with a 5-pound box. They'll balance if it's 20 inches away. And I can sit there and I can play with all of these different forces. In fact, let's do one more of these before I jump into the much more complicated and much more real scenario we're going to use to actually balance an aircraft. Let's consider that we have another teeter-totter, and on this teeter-totter, I have a box. We're going to call it A because I'm real creative. And over on the other side, I have a box B and a box C. All right, how are these going to play with each other? Once again, we're going to put some distances in, and I'm going to call this distance A. And I'm going to come over here, and we're going to have a distance B. And then I need a distance C, and distance C is going to be measured all the way from my fulcrum. All of my distances need to be measured from my fulcrum to be actual, real things that matter. And what do I know? I know that my moment A, if this is going to balance, must be equal to my moment B plus my moment C. All right, because these two are both going to try and twist the whole system this way, and A is going to try and twist the system that way. And for both of those to be equal to each other, I can start throwing some numbers in here, and I can figure out exactly what they are. Just for the fun of it, let's do that. Let's put some numbers in here. I think that my box A could be equal to, let's go with 20 pounds. And my box B could be equal to 5 pounds. And my box C could be equal to 15 pounds. I'm just throwing some numbers out there to make this into a real problem. Now, let's go with our distance A, and let's say that A happens to be 20 inches, and B happens to be, oh, how about we go with, that looks like about half the distance. Let's go with about 10 inches for B. And I want to know, how far do I have to set out this box C to balance on this side? All right, on my side A, all the way over here, I have 20 inches times 20 pounds, and that's equal to 400 inch-pounds. Okay, on this side, I have 10 times 5, I have 50 inch-pounds, plus, how many inch-pounds do I get out of my box C? I get 15C inch-pounds. All right, I'm going to leave off the inch-pounds because we don't really need to work with these units right now. I get 400 minus 50, because I'm going to subtract 50 from both sides, is equal to 15C. And that's how much distance I'm going to need for C. Or in this case, I get 350 equals 15C, and therefore 350 over 15 equals C. All right, so now I need my calculator to do that because I'm not near as good at math as I used to be back before we had calculators. But my little calculator is very capable of telling me, calculator, clear 350 divided by 15, and that tells me at 23 1/3 inches, C equals 23 1/3 inches. Dash, dash for inches. All right, so you may say, yeah, that big whoop, that doesn't really help me. Well, that's important because that gives us an idea of why things are happening. But let's consider now, instead of an invisible teeter-totter that doesn't have any mass and just sits here on the board, let's consider an actual airplane. On our actual airplane, we're going to kind of regard the airplane as a teeter-totter, and we are going to set the airplane up, and we are going to put it in a place that it's going to balance. Let me try and draw a little better airplane this time. Sometimes I can draw decent airplanes. More often than not, they look all the same. Okay, here's our airplane. Here's our little airplane. We'll make it big and tall in tricycle gear. And it has a center of gravity somewhere. And I can find its center of gravity, the center of mass, where this would just kind of hang suspended in the air. I can find that center of mass by looking inside and finding the weight and balance report. And the weight and balance report is going to tell me something about that airplane, and it's going to tell me the weight and the center of gravity point. So let's say that on this particular airplane, I read that its weight is 1,510 pounds, just making stuff up off the top of my head. Can you guys see that? Yes, 1,510 pounds. And then we need a center of gravity figure, and let's put that at 25 inches. Now, you may ask, where's the 25 inches come from? Well, somebody somewhere had to pick something to measure from, and we're going to say they're measuring from right here at the firewall, and that's 25 inches behind the firewall is where they say that this airplane balances. And what that means is if I could actually grab this airplane and suspend it by a string from there, it would literally balance. That's what the center of gravity means. And I know this airplane already has this information because I found it on the weight and balance report. And of course, we have to keep the weight and balance report updated. If we don't have our weight and balance report, our aircraft's not allowed to fly. And it wouldn't fly very well. Now let's consider we're going to put something in this aircraft. And in this particular case, let's put a piece of baggage into the back of the aircraft. Let's put a suitcase back here. In this suitcase, we're going to make this suitcase, okay, suitcase equals 100 pounds, because I like things that are nice and neat. All right, 100-pound suitcase. I need to know where the suitcase is going to go in order to know how that's going to affect the aircraft. Because if I put the suitcase right at the center, right where it's already balancing, I could still balance the aircraft that way. But we're probably not going to end up with the suitcase right there. We're probably going to put the suitcase in the baggage compartment. And let's say on this particular aircraft, we look it up and we find that the baggage compartment is at 96 inches. All right, 96 inches. You may go, big freaking whoop. Well, that helps me to know how much moment, how much twisting force that suitcase is going to generate on the aircraft. And so I need to put that suitcase into that position. I'm going to go, the moment of S for the suitcase is equal to 100 pounds times 96 inches, which is equal to 9600 inch-pounds. That's how much twisting force this suitcase is going to exert on this aircraft when it's sitting right there. But how much is it going to actually make the aircraft change its center of gravity? That depends on something really, really big. And in this case, it's how big is the airplane. And a big airplane like a Boeing 747, if you put one suitcase in it, it's hardly going to change it at all. But if you take a little tiny bitty airplane, like a little model airplane, and put a huge 100-pound suitcase on it, it's going to be a huge change. So we need to know how the airplane plays into this. And to understand how the airplane plays into this, we need to keep track of the moment due to the airplane. Now, this is going to seem a bit weird, okay, but I have my moment for my suitcase. Now I want my moment for my airplane. I'm going to call it M sub A. And it is equal to 1510, a lot more than the suitcase, times the inches on my center of gravity, on my aircraft, because that's where this aircraft is centered. Once again, I need my handy-dandy calculator. 1510 times 25 inches, and it gives me a moment of 37,750. All right, my moment of my airplane is 37,750 inch-pounds. Okay, you may ask yourself this. Why does my airplane have a moment if it balanced somewhere? Well, everything has a moment. It just depends on where we consider the zero to be. What I need to do is I need to consider how those two moments are going to go together. And remember where we had two boxes over here? We just added the two moments? I can do the same thing in this case. My total moment then is going to be the 37,750. They're both trying to twist this airplane back onto its tail, plus 9600. I have a total moment of 36240. No, that's clearly wrong. Let's try again. 37,750 plus 9600. How about 47,350? 47,350. My moment total, and I want to write this in black because we're going to try and keep it, is equal to 47,350? Yes. 47,350 inch-pounds. And if my airplane were sitting right here, remember it would go ahead and fall. But I don't want my airplane to be sitting in that particular position. I'm going to consider what would happen if how I would find exactly where this airplane actually balances now. Okay, so it started out balancing at 25, but I want to know where it balances right now. Remember, it had 1510 pounds. I shouldn't have erased that. 1510 pounds, 25 inches. That was how our aircraft started out. But I want to know what happened to its center of gravity. And to do that, I'm going to consider that by adding these two together, I find out that the total moment that this aircraft has right now is 47,350. And if I take the total moment divided by the total weight of the aircraft and the baggage, I'm going to find out what that new center of gravity is. So I had 1,510 pounds of the aircraft and 100 pounds of the suitcase, gives me a total of 1,610 pounds total. And if I take my total moment divided by my total number of pounds, I'm going to get what my total is going to, what my total arm or average arm would be. So 47,350 divided by 1,610 gives me a total of 29.4. All right, my 29.4 is my average arm. Okay, and that average arm is really important because that says that if I could replace both of these with one item, it would have the same amount of torque as if that item were centered the same weight as the airplane, centered 29.4 inches back behind the datum. And what that means is if I were to take my balance arm and I were to try and suspend it from something that was 29.4 inches behind the datum, it would exactly balance. And I know this may seem kind of roundabout, but that's literally what we are going to do when we try and figure out what the weight and balance is for our aircraft. Now, there are lots of ways to calculate the weight and balance on the aircraft. There are all kinds of different things that we can do, but the easiest way to do a weight and balance is to make a table and keep track of these things. Because as you can see, when I write these things down, they get rather scattered all over my piece of paper or my board in this case. But if I make myself a nice, neat little table, I can keep track of this a lot better. And I'm going to call my table this: item, weight, arm, moment. I got 4 columns in my table. And in this table, I'm going to keep track of all the things in this 4 columns, and that's going to help me to keep track of everything. And then at the very end, I'm going to total everything up. Let's consider that we have an airplane, and I'm going to try and do this one will make a really crappy little airplane. All right, here we are. There's our little airplane. Our little airplane has an empty weight, EW equals 1,212 pounds. Just to throw out some numbers. Okay, our EWCG, our center of gravity at the empty weight, I'm going to throw out as 39 inches. And I am going to load this aircraft, and we're going to consider several different things that we want to put on this aircraft in order to figure out what it's going to have. And I think that we need, well, first of all, we always start with the plane. Okay, so in our table we have the plane, and its weight was 1212. And its arm was 39. Then the next thing we want to do is consider what else we need to put in the plane. And I suggest we put a pilot in the plane before we go and fly. And we're going to put a pilot in the plane, and I'm going to pick, just because I happen to like 200 pounds, we're going to put a 200-pound pilot in the plane, and we're going to assume that the pilot sits just a little behind the CG, let's say at 43 inches. We can find that in the weight and balance data. Or we can measure it with a tape measure and figure out where the pilot sits. But let's say the pilot's sitting there at 43 inches. And before the pilot gets to go fly, the pilot also needs probably some fuel. So let's put a little fuel on this airplane. In this case, let's say we put 10 gallons of fuel on the plane. A gallon of fuel weighs 6 pounds per gallon, so that's 60 pounds of fuel. Be careful with your fuel. You always got to make sure it's in pounds when you put it in this chart. And our fuel tanks are going to be located at 40 inches. This is something you would find on your type certificate data sheet or something on your airplane, figure out where your fuel goes. And do we need anything else to go fly? Let's say the guy's going out and flying somewhere, so he's going to take a 20-pound overnight bag. So we're going to put bag, 20 pounds, and our baggage is going to go sit behind him. Let's say it's about 20 inches behind him, so how about 63 inches? There are some realistic numbers for us to work with. What is the center of gravity of this aircraft? Well, we need to know what the moment is for everything before we can do that. And we've got our columns all set up. Now I'm going to go ahead and put everything into the calculator. We got 12 times 39, which tells us we have 47,268. These numbers get pretty big. 47,268 is our moment due to our aircraft. Our moment due to our pilot is 200, and it is times 43, gives me 8,600. Our moment due to our fuel is 60 times 4, that's 2,400. And our moment due to our baggage is 126 with a 0 after it. 1, 2, nope, that's not right. I better use the calculator. Okay, 20 times 63. I was right, 1260. Should have trusted myself. And these are the moments for everything inside of our aircraft in this nice little table that I can keep track of and I can figure things out. Once I know all of these, I need to get the total moment, and the total moment I'm going to get by adding all of these and putting it down inside this column. So, 1260 plus 2400 plus 8600 plus 47268 gives me a total moment of 59528. 59528. And once I've got that, I need to know, I'm going to have to divide that by the total weight, so I need to know my total weight. I'm going to total all of these, and I've got 12, 12, 14, 12, 14, 72, 1492. Whoa, in 1492, Columbus may have sailed the ocean blue, but we're going to see if our airplane can go sailing into the blue at 1492. So I now take my total moment divided by my total weight, 59528, divided by 1492, and that tells me that my total my average CG now, the average moment of all of these, averages out to 39.89, or we'll say 39.90. Now this is not a total. This is an average figure across that. And I have to be careful when I say that, but this is my new CG, 39.90, and it is equal to the total weight divided by the total moment of all the items on the weight. And that is the place where I could now rebalance my airplane at 39.90. Now, let's check and see if that's realistic. I started at 39 inches. I loaded everything. They're smaller than the airplane. They're loaded just a little behind. So yeah, that makes sense. By the way, on our airplane, we say that in this direction, it is positive, and in this direction is negative. And that keeps track of our directions as which we go, so we don't have to go, this one is equal to that one and all this. We use our positives and our negatives, and everything keeps track of itself. And that is how we work a basic weight and balance problem. We put a 4-column table, we add all the weights, we put in the arms, we get all the moments, we total the moments, we total the weights, and then we divide the total moment by the total weight to get our answer. And believe it or not, this will find the answer to just almost any problem that you have. Let's consider if you wanted to remove something from the aircraft. Let's say that you were out trying to fly and you decided that you needed to take the seat out of the plane. Now, hopefully this is a home built, because I don't know that you're allowed to take the seat out of a plane if it's not a home built. But if you were to go to take the seat out of the plane, could we figure it out on this table? Sure we could. Okay, we'd come to where it is a weight, and we would put a negative weight in for the fact that we removed the seat. And if I remove something, the weight becomes a negative. We already said that the arm is positive if it's back in back of the datum, and it's negative if it's in front of the datum. And so we have two columns that can be positive or negative, and our moment can then be positive or negative as well, and that keeps track of which direction it's trying to spin things. And this keeps track of just about everything. In fact, it keeps track of everything. And the only type of problem I cannot answer with this table is I cannot answer a problem where I'm trying to figure out how much weight would it take to move. So a shifting weight problem is not simple enough to use the table on, and a ballast problem where I'm trying to shift a weight a certain amount or shift the CG, for those I'm going to need different formulas. But as long as I'm not trying to do that, this table will solve everything. There's a lot of people who go out and they get, oh, this is the formula that you use, and they have these big, long, crazy formulas. You don't need all of that. Just make yourself the table, chug your way through the table, and you will get your weight and balance. And so that's what we're getting ready to do. For my class that I'm making this video for, well, they've got lots and lots of tables to calculate. And on the first lab that they're going to do, first of all, they're going to work the levers. And then after they're done working the levers, they're going to work an airplane. And then they're going to start using the table to work much more complicated airplane problems. And after they're done with that first set of with more complicated loading problems, then they're going to have to start taking things off planes and putting things on planes, because they're going to be mechanics, and mechanics do take things off of planes and put things on planes. But that's what we're going to be working on doing, and hopefully if you are watching along, you figured something out as well. That's all I got for today. Have a good one.